Okay, here is the idea. You have a 10 kilogram ball, it's 10 meters above the surface of the earth, and you drop it on a 1 meter long spring, and it compresses the spring so much that the compression is virtually the same as the entire length of the spring. We are going to use a potential energy setup or a work energy setup, and the system will be the earth, the ball, and the spring. And let's see how that looks if we try to solve for the stiffness of this theoretical spring. All right. So we start from work equals delta E, and components of delta E are the change in kinetic energy, the change in potential gravitational energy, the change in the potential spring energy. Okay. And we'll expand those each of those three components to final minus initial, and do our algebra. And so we'll have our work plus our three initial components equals our three final components. Expand those formulas, and the work will go to 0. The the initial velocity will bring the initial kinetic energy to 0. The initial gravitational potential gravitational energy is like 980 joules. And the initial spring, because it's not stretched, it goes to 0. The final velocity is 0 because it stops as it reaches, the surface of the earth. The ball does, that is. And because the spring is 1 meter long and completely compressed, we can technically say that the gravitational potential final energy goes to 0, and that leaves us with our potential final energy of this compressed spring, which is 1/2 the constant, and the stretch is 1 meter squared. So here we have our 980, we'll write it as Newton meters, equals 1/2 meter squared, right? 1/2 times 1 meter equals 1 meter squared, equals 1/2 meter squared ks. Divide each side by 1/2 meter squared, and your spring constant in the typical units will be 1960 Newton meters. Okay.